Today, we are also going to learn about tangential versus centripetal acceleration. Really, we already know about tangential acceleration. Tangential acceleration is an acceleration in a straight line. Centripetal acceleration, however, is something else. To talk about centripetal accelerations, we need to talk about centripetal forces. There's a relationship between force and acceleration, which you already know, and that's going to hold true here. Any force that points inward is a centripetal force. Now, a lot of people learn a lot of different things in the course of just living their lives. They hear these expressions on TV, they hear it from high school science teachers, things like that. And I want to make sure that everyone is on the same page with this. There is no special force called a centripetal force. Literally anything that points inward is a centripetal force. If I push this like that, this is a positive x force, right? I'm pushing this in the positive x direction, like that, positive x direction. Do I have a special name for a force that points in the positive x direction? Not really. It's just it points in the positive x direction. I guess if I'm doing an equation with it, I'd say that F net x is max. That's how I would use this to solve a problem mathematically. But I don't really have a special name for a force that points in the positive x direction, or the positive y direction, or the negative y direction, or anything like that. For historical reasons, we do have a special name for forces that point in the centripetal direction, which is the inward pointing direction. Centripetal is a word that comes from Latin. It's made of two different words. You can think centripetal, centripetal. Centri means center, C-E-N-T-R-I, that means center. Pedal is from, there's a lot of different words that come from pedal. The closest related one would be something like petition. To petition means, to sign a petition, what are you doing? You are seeking something. If you petition the government for redress of grievances, then you are seeking change from the government. Petition means to seek something. A petal, a flower petal, seeks the center of the flower, or the sun. Actually, I don't know which way the etymology goes, but it might be that it's seeking the sun, now that I think about it. Petals seek something, and I guess it might be the sun. I don't know. But centripetal means center seeking. Any force that points towards the center of a rotation is going to be a centripetal force. There is no special force that comes in the universe and says, oh, something is going in a circle, I've got to point inward. I'm a force that's going to point inward. No, there's nothing like that in the universe that does that. There always has to be some force that already exists that points inward. The easiest thing to probably think about is a yo-yo. If I had a yo-yo here, I would demonstrate with the yo-yo, but I don't. Imagine a yo-yo spinning in a circle like that. Well, to spin it in a circle, you have to hold onto the string. You're holding onto the string, and you're spinning the yo-yo in some wide circle like that. What force is keeping the yo-yo going in the circle? Well, that has to be the tension of the string. The yo-yo is at the end of a string. The string always has a tension force with it, and that force always points to the center because the string points to the center. As a yo-yo goes around a circle, the tension always points inward. That inward pointing force keeps the yo-yo in that circle. If you snipped the string, what would the yo-yo do? It would just go and it'd fly off somewhere. But because the string is there holding on to the yo-yo, it keeps going in that nice circle as you spin it around like crazy. And that force of tension that's keeping it doing that is a force that points inwards at all times. Thus, the tension is the centripetal force. We didn't have to create a new force. The universe didn't like come in and cause new forces to happen when you're spinning a yo-yo around. It's just, well, there's tension there, and tension points inward. And if a force points inward into the center of the rotation, then it's a centripetal force. It is a force that is seeking the center. So when you hear an expression like centripetal force, don't think that there's a special kind of force, like the normal force or like tension or like gravity. It's not a force like that. It's a direction of a force, like an x-directed force or a negative y force or something like that. That's the same meaning as centripetal force, because centripetal really is just a direction of a force rather than a type of force. Now that we've talked about centripetal forces, we can talk about centripetal accelerations. If an x force, a force in the x direction, would cause an object to accelerate in the x direction, then a centripetal force would cause an object to accelerate in a centripetal direction or a center-seeking direction. Gravity is an excellent example of a centripetal force because it's a force pointing towards the center of the Earth. Now, on the surface of the Earth, we've got the normal force, and we're kind of attached to the Earth in a way. And so we're going to be rotated around the Earth just like, you know, a mountain is rotated around the Earth as the Earth rotates. If you want to think of gravity as being a centripetal force which induces a centripetal acceleration, think about the moon orbiting the Earth. If you just imagine the moon. Now, the moon, there's no other forces acting on the moon other than gravity. And so it just becomes easier to think about when you've only got the one force that you have to worry about. And so as the moon goes around the Earth, there's only one force causing that to happen, and that's gravity, and that gravitational force points towards the center. And because there's a gravitational force pointing towards the center, there's also an acceleration pointing towards the center. This also bothers people, that there can be an acceleration pointing towards the center. So I'm going to take my trusty Lego contraption and spin it around like that. And at any given point along its spin, there is a force pointing towards the center. You know, if I spun this too fast, if I really went wild with this and spun it too fast, well, this would pop right off like that. There has to be some force holding this on to the contraption. It ends up actually being friction in this case, of all things. Like if the centripetal acceleration is trying to get it to slide off like that, it's friction that's holding it on. So actually, as I spin this around, the thing that's holding it together, the thing that's keeping it going, the thing that's keeping it held together and going around the circle is a force of friction holding the things from, you know, it's holding things that way because they want to fly off that way as you spin it around and goes whoop, and it flies off. No, we don't want that. Held together by friction, so friction is the centripetal force. Now, as we go around in a circle, you can see that if I could do this better, the velocity could be held constant. I could hold the physical velocity, the speed, excuse me. I could hold the speed constant as I go around the circle, because I could go around the circle at, you know, half a mile per hour. I have no idea how fast this is going. Half a mile per hour around the circle, a quarter of a meter per second around the circle. Sure, that works. Well, its speed is constant, but its direction keeps changing. When you're here, the direction of your velocity is out that way. But by the time you're here, the direction of your velocity is like that. As I move from here to here, my velocity goes from this to this. And when I'm here, the velocity is down. When I'm here, the velocity is that way, as I'm going around the circle, like that. So the velocity is always staying the same amount, but changing direction. If I wanted to take a velocity that was like this and shift it to a velocity like this, I want to take a velocity like that and make it more like that. That's my goal. Well, to do that, I need to add a little bit of negative. To get a velocity going from like this to like this, I need to add negative like that. Velocity originally looks like this. I want it to look like that. So I have to give it some negative like that. That means as this goes around like that, we're getting negative velocities like that, or downward diagonal velocities like that. I had to add some sort of downward velocity to it. To change its velocity from going like that to going like that, I had to add some down. That down came from this. It came from the pull that this has on this part, that this support has on the rest of this pulled on the rest of this with some downward force, which caused a downward acceleration. Just moving at a constant speed like this ends up going, well, in this case, you're going like from this velocity, that direction, down to that kind of direction. And so you had to change something that was going like this to going like this. And that obviously takes some downward acceleration to get a velocity to change from that to that. It took a downward acceleration to change that. You can think about that at any point along its motion. If you're here, then you've got a velocity pointed like that. And when you are here, you've got a velocity pointed like that. And so you went from this velocity to this velocity. And to go from this velocity to this velocity, you had to have a velocity inward, or sorry, an acceleration inward. So as you go from here to here, you had to have an acceleration this way. Hey, look, towards the center. If I go from this to this, I go from this to this, I had to have an acceleration that way. That way is right towards the center. That's what we mean when we say a centripetal acceleration. You can have an acceleration towards the center of your rotation without actually spiraling inward. And if I keep spinning this, the end of it doesn't like spiral in and get like sucked into the middle like a black hole. It stays at the same distance, that same radial distance. That is perfectly okay for that to happen, for it to not spin on into the center. And that's because you're just changing the direction of the velocity as you go around. There's an equation that we can use to define this and describe this. The centripetal acceleration is equal to the velocity that you're going around the circle squared divided by the radius of the circle. We can also say that the centripetal acceleration is equal to the radius of the circle times the angular velocity that you're going around the circle, the radians per second that you're going around the circle. Notice AC, acceleration centripetal. This is not really a new kind of acceleration. This is an acceleration that we've worked with before. This is just the same as any other acceleration that we've worked with before, except for specifying that it points inwards. Centripetal means inwards. So we had AX before, and we had AY before, and AY was usually negative 9.8 meters per second squared because of gravity. So we had AX and AY. Those represented the accelerations in two different directions, the X direction and the Y direction. Now we're adding in acceleration in the centripetal direction or the inward direction. This works the exact same way as anything else except inward. In fact, it has the same units. Centripetal acceleration has the same units as acceleration in X or acceleration in Y. Centripetal acceleration is measured in meters per second squared. It's not a theta thing. It's not a radians thing. Centripetal acceleration is meters per second squared. This is measuring not its change in speed, but its change in direction. A greater centripetal acceleration means that you're changing direction faster, not speed, you're changing direction faster. And as I say here, it is very different from angular acceleration. It has different units than angular acceleration. To have an angular acceleration, you need to start off slow and speed up in your circle. But you can have centripetal acceleration at any speed, and at any constant speed, you can have a centripetal acceleration because you're always changing direction. And changing direction is a way of changing your velocity, and any change of velocity is an acceleration. Questions for you to think about. Let's imagine you are driving at a constant speed and constant direction on a highway. So you're on the highway, constant speed, constant direction. That implies that the net force is equal to 0. If you're not changing your velocity at all, then you have no acceleration, and so your net force has to be 0. But now the road gently turns beneath you, like you're coming into a turn. And so what do you have to do? You have to turn your tires to turn with the road. But how does that make your car turn? Just by changing the direction of your tires, your car starts turning? Well, that's actually because of friction. The friction that your tires have with the road will actually point inward. If you change the direction of your tires from that to that, then suddenly you have an extra term of friction pointing that way. So if you want to turn to the right, like that, then you turn your tires to the right, like that, and you get a rightward force from the friction between your tires and the road. That supplies a centripetal acceleration, because that's going to be pointing into the center of the circle that you're now making as you go around that curve. Pointing towards the center at any point as you go around that curve, it's a centripetal force which induces that centripetal acceleration and means that you can go in a circle. If you're going in a whole circle, you usually don't do that. So you just, you straighten out your tires once you get the direction you want to go. Your speed can be constant around this entire circle, but your direction is changing. And if your direction is changing, you must be accelerating. And if you're accelerating, there must be a net force on you. And if you're accelerating centripetally towards the center of the circle, then it must be a centripetal force. Here's a diagram of what I'm trying to explain. You've got a velocity forward, but you want to change the velocity to be tilted. So as you go around the circle, 1 second later, you're going to have the velocity be a little bit more tilted in the downward direction-ish. And so you have to have an acceleration to give you that. You have to have an acceleration changing the direction of your velocity. Not the amount of your velocity, just its direction, so that the velocity points in a different direction later on. Let's do an example with this. On this merry-go-round. Sadly, you board Pennywise's merry-go-round. You sit at the outside edge 3 meters from the center. The angular speed of this merry-go-round is 19 radians per second. What centripetal acceleration do you experience? And how does this compare to the acceleration due to gravity? So here's the problem. We've got a merry-go-round that you don't want to board because it's made by that creepy clown. There's you being supported by some sort of support that I drew in there for some reason. The angular velocity of this merry-go-round is 19 radians per second, and you are 3 meters from the center. We need to find the centripetal acceleration that you experience on this merry-go-round. Well, it's actually not too bad to calculate this, because we can just take the equations that we've been given. So centripetal acceleration is equal to v squared over r, or we can say centripetal acceleration is equal to r omega squared. We can do either one, of course. And so let's just do centripetal acceleration is r omega squared because we've got that. We've got r and we've got omega. So r, 3, omega, 19, squared, we're squaring 19, and then multiplying by 3. Our centripetal acceleration is 1,083 meters per second squared. We can compare that to gravity by just dividing it by 9.8. It's 110 Gs of acceleration. You've heard of fighter pilots and whatnot that can pull 10 Gs or something. That means that they are experiencing an acceleration equivalent to 10 times the acceleration that they'd face just at the surface of the Earth. This is 110 times the acceleration you'd face at the surface of the Earth. So yeah, you're not doing well with that kind of acceleration right there. I want to talk about this equation up here very briefly. I just want to show that these are all correctly equal to each other. And so actually I'll start with this. I can start with centripetal acceleration is equal to r omega squared. And then I can say, oh yeah, omega is equal to v over r. So I'm going to replace omega with v over r. And so I keep the r. I've got omega squared, which becomes v squared over r squared. I get to get rid of an r there. And so now I've got v squared over r, but I already know that v squared over r is equal to centripetal acceleration, just like that. So this is how you can prove that this is equal to that, and that is equal to that, and this is equal to that, and everything is equal to each other. This is how you prove that right there. Next example. We've got a 1,200 kilogram car trying to make a wide turn on a slick road. It's been raining, which it has in real life, it's been raining. The radius of curvature of this curve in the road is 50 meters. The coefficient of friction with the road is less than it usually is. It's now just 0.3. The only force which can act centripetally is friction. The only force that can keep you going towards the center is friction. What is the maximum speed of this car around this loop without it flying off and going off the road? Here's our setup. We've got a road that's curving. We've got a curve and a road. We've got our car right there. The radius of curvature of the road is 50 meters. That means that if the road kept curving the way that it was, it would just get around in a curve of radius 50 meters, a circle radius 50 meters. Mu is 0.3, the coefficient of static friction, 0.3. The mass of the car is 1,200 kilograms. We need to find the velocity, the highest velocity that the car can go around that circle without spinning off. You can imagine, in order to change your velocity from going in that direction to going in that direction, you're going to need a force inward, and that force inward is going to be from friction. If you don't have that force inward, you're not going to be able to change your direction. If you can't change your direction, well, you're just going to go off-road like that. You need the friction with the road in order to change your direction from that direction to that direction to stay on the road. Our force of friction is the thing that points inwards. This is a top view of the situation. This is the view from, let's say, behind the car. So this is what the free body diagram would look like from, trailing behind the car, for example. Your force of friction points inward. The center of rotation is somewhere over here. The force of gravity points down, the force of normal points up. And we need to find Vmax to solve this. What can we do? We first acknowledge that the only centripetal force is the force of friction. The force of friction is equal to mu times the normal force. We can see here that the normal force should be equal to the force of gravity, and the force of gravity is equal to the mass times the acceleration due to gravity. So I'm just going to go through this quick. Force of friction is equal to mu n, but n is mg, so force of friction is mu mg. Now, I can pull out this equation. Hey, this equation. We have not written it down like this before, but this is true. Remember, we had F net x is equal to max. F net y is equal to may. X and y are directions. Centripetal is a direction. Therefore, F net c is equal to mac. It's the exact same idea as we had with x and y versions of this. The only force that points inward is the force of friction. So the force of friction is the net centripetal force. If we had another force going out, then we'd have to have like minus whatever that thing was because it's going the opposite direction. But we don't. So we don't have to include that. Maybe we've got a little rocket engine on our car that's, pushing us inward somehow. Then we'd have, plus some additional force in there on top of the force of friction, but we don't. So we've just got force of friction pointing inward. That's equal to the mass times the velocity squared over r. Remember, centripetal acceleration is v squared over r. So we can replace acceleration with v squared over r. We can replace force of friction with mu mg right there. That's equal to the mass times v squared over r. We can cancel out a mass from each, divide both sides by m. Mu g is equal to v squared over r. We can solve for v, square root of mu gr, and we find the velocity that you can be going on this is equal to the square root of 0.3 times 9.8 times 50. And so we have our maximum velocity around this curve, 12.1 meters per second. In this diagram, the force of friction is pointing in the positive x direction. But the way that I've drawn this, the center is somewhere over here. So instead of calling it positive x, I'm going to say that this direction is the centripetal direction. Instead of saying it's the positive x direction, this is the centripetal direction because this is the direction towards the center of the circle that we're making. Then, why does gravity matter at all? Gravity matters because we had that the normal is equal to mg. And so if normal is equal to mg, then we've got a force of gravity that we have to deal with because the normal is somehow proportional to the friction. If you go to another planet and if everything is heavier on this other planet, if there's more force of gravity, then it would feel like there's more friction everywhere because it would be harder to move a heavier object across something than it is on a lighter planet where it'd be just very gentle moves one thing across another. So gravity actually does contribute to friction this way. It's that the friction is equal to the mu times the normal force. The more force that you're pressing down on something, the harder it is to move across. But if you're pressing down just very, very lightly, it's very easy to move across two things. So the more downward force that you have from gravity or whatever, the more upward force you're going to have from the normal, and therefore the more friction you're going to have based on this equation. We've already talked a little bit about how we feel weight thanks to that fish in that elevator. The way we feel weight is by how much normal force we have on us. The more normal force we have on us, the more weight we feel like we have. It doesn't actually change the force of gravity on us. It doesn't give us force of gravity where we didn't have it before. But to us, we feel weight by just how much normal force is pointing up on us. Let's use what we know here. I hope that everyone has seen the movie Interstellar. I myself really enjoyed this movie. I thought it was a fun movie. A lot of the people that I knew were confused by these scenes that happened in this crazy looking town that wraps around itself. This looks like something right out of Inception, which is another movie that I enjoyed. but the sky curves around like this. How is that even possible? How do things that are on the ceiling of this not fall to the floor of this? Well, it's because this whole thing is spinning. This kind of space station was designed by NASA back in the 70s. And so this is what NASA envisioned back in the 70s. Envisioned gigantic rotating space stations that had panels of land with panels of glass in between the panels of land. And the plan was to build these so that the diameter of one of these cylinders, this is a view from inside the cylinder, one cylinder would be 4 kilometers, or about 3 miles in diameter, and 20 kilometers, or 12 miles long. You could fit a nice sized city in one of these space stations, and you'd have like green grass and trees and rivers and suburbs and things like that. I think that'd be awesome. So I want to build one, because of course I do. I want to build a spinning space station with artificial gravity, and I want to experience Earth-like effective gravity, 9.8 meters per second squared, but I've heard that you get dizzy if you're spinning too fast. That totally makes sense, that if you're spinning fast, you get dizzy. So if you make more than one rotation every 30 seconds, you're going to get dizzy. So that is going to affect how large of a space station I need to build. Here I have the space station that I want to build, and you can see everyone is kind of just like sitting there on the outer edge of the space station. Each of them is going to be experiencing a normal force pointing inwards. They all think that the outer edge of the space station is the floor, and so they all get an inward pointing normal force. That inward pointing normal force is the centripetal force, because it's pointing towards the center of the space station. If we have an inward pointing centripetal force, then we're going to have a centripetal acceleration, of course. I want that centripetal acceleration to be 9.8 meters per second squared, because I want all these people to feel like they have a normal weight. And the way we feel weight is through the normal force on us. So give them a centripetal acceleration of 9.8 meters per second squared, and they feel like it's just completely normal. If you're in a space station like this, that was spinning, and if it was spinning at the right rate, you would not be able to tell that you were not on Earth. You know, unless you did some careful experiments, you would not be able to tell that you were not on Earth. You'd be able to walk around normally on this space station. I said that if you do more than one rotation in 30 seconds, then you get dizzy. So let's just set it to be one rotation in 30 seconds. I want to find out how large of a space station I need to build. So I need to find whatever radius would give you one rotation in 30 seconds and a centripetal acceleration of 9.8 meters per second squared. So I say centripetal acceleration is equal to v squared over r is equal to r omega squared. Probably easier to use this, because I know that one rotation in 30 seconds, we can convert this into omega eventually. So let's do that. We need to find out what omega is. So I know that I need one rotation in 30 seconds, one rotation per 30 seconds. I need to get this into radians per second, because we always needed things in radians per second. So that's going to be 2 pi radians. One rotation is 2 pi radians. So 2 pi radians over one rotation, that's equal to 1, which is fine to multiply by. But I can get rid of that rotation and that rotation. So 2 pi radians divided by 30 seconds is 0.209 radians per second. I can plug this up into there, into that equation, and I can plug my 9.8 in for centripetal acceleration. So that's equal to r times 0.209 all squared, and we get that the radius that we need on the space station is 224 meters. In order to build a space station that is large enough that it can rotate without the residents of that space station to get dizzy, and large enough that you experience Earth-like gravity, you need to build it pretty large. You know, that's the radius. So the diameter is going to be nearly 0.5 kilometer. That's the diameter of this kind of space station, 0.5 kilometer. That's a very large space station right there. A roller coaster has a loop with a diameter of 14 meters. How fast do you need the cars to go around the loop for them to barely make it around the loop? For the car to barely go around the loop, the normal force at the top of the loop must be very, very small, effectively 0. We want to have a roller coaster go around the loop, and we want a roller coaster car to go around the loop, and we want the normal force on that roller coaster to be 0. So we can draw a side view of our roller coaster. So the car comes in here, it goes around the loop like that, and then it exits over there. And here we are at the very top of the loop. Radius is 14 meters. The normal force needs to be 0. And so we can draw a free body diagram of the cart when it's at the top. Well, normally, you know, the cart is just barely touching the rail right there on the roller coaster. And so normally that would mean that it should have a normal force. But I'm saying that the normal force needs to be 0. So we're not going to draw normal force here. We're just going to draw the other forces that are acting on it. We're going to say that, okay, it's low friction, I guess. We're going to say, okay, there's definitely gravity acting on it. The gravity is pointing down. And that's it. There's really no other forces acting on this. Therefore, look at this. The centripetal force is gravity. Gravity points towards the center of this. Gravity is our centripetal force on a roller coaster loop. Gravity is the only centripetal force. So I can pull out this equation again. F net c, the net centripetal force, is equal to the mass times the centripetal acceleration. I'm going to have the force of gravity be a positive number here. Centripetal means towards the center. Just like positive x means positive x and positive y means positive y, centripetal means towards the center. Gravity is pointed towards the center. Therefore, it gets a positive amount. If a force points towards the center and you're doing a centripetal force equation, then it gets to be positive. Even if it's pointing down, well, towards the center, no matter where you are, towards the center is going to be the positive force. Away from the center would be negative, but we're pointing towards the center, so our force of gravity is going to be listed as a positive force because it is towards the center. It's going to equal the mass times AC, which is v squared over r. Force of gravity is mass times gravity acceleration. We can divide both sides by m. Do a little bit of rearranging. You find that the velocity squared is equal to g times r. Velocity is equal to square root of gr. Plug in the numbers, and you get that the velocity that you have to be going around this roller coaster loop is 11.7 meters per second. If you're not going that fast, then you'd go around the loop partially and then go meh, and fall off like that. There'd be somewhere that you'd disconnect from the track and you'd fall off the track like that. You need to be going fast enough so that you can go just in the circle like that. This is regardless of mass because we were able to cancel out the mass there. Very, very often we get to cancel out masses, which is great. It shows that if you have a heavy object and a light object, and you drop them at the same time, they hit the ground at the same speed. It's the same principle as that a heavy object and a light object will hit the ground at the same speed if released from the same height and all that.